and structural stiffness matrices. Now, the kinematically indeterminacy already we discussed. Now, combining the stiffness matrix of the individual members can generate the stiffness matrix of a structure. What does this mean? Now, first we need to generate the stiffness matrix for the element. And then from the element, we will combine their effects, and then we will generate the stiffness matrix of the structure, which will be the structural stiffness matrix. However, the combining process should be carried out by identifying the truss joint so that matrix elements associated at particular member stiffness matrices are combined. So from the element stiffness matrix, while making the structural stiffness matrix, we need to put the element of elemental stiffness matrix in a proper and organized way so that we can formulate the structural stiffness matrix. To the structural stiffness matrix, now the elements will be transferred from this elemental stiffness matrix to their appropriate addresses. And we will discuss this when we get to the problem or when we get to the examples. The procedure of formation of structural stiffness matrix is as follows. So let's now see. First, what we do, individual element stiffness matrix for each member. This is constructed. The method of formation of elemental matrix has been explained in last module. Let we have a member as shown, then element matrix is given as, so this is now an element. If you remember, it used to be element number 7 in the truss. We picked this one up. We designated this as joint J. This was joint K. The global displacement at joint J were D1 and D2, and the global displacements at joint K were D3 and D4. In element axis or member axis or local axis, the X, this was the local X axis, this was the local Y axis of this member. X axis was along the longitudinal axis of the member. And the global the local displacements, if you remember, in the direction of this longitudinal at the J end, it was XM1, and this was YM1. At this end, it was XM2, and this was YM2. The projections we defined, how much is the horizontal projection in terms of the X coordinates, how much is the vertical projection in terms of the Y coordinates. Then theta was counterclockwise. It was measured from the positive X-axis in the counterclockwise direction. And then this was theta, so cos theta was equal to, it was this we need to change now. This is actually cos theta. This has to be, this is cos theta and this is sin theta. Already you know this. We discussed this, that cos theta is equal to xk minus xj divided by L, and sin theta is equal to yk minus yj divided by L. So this was the definition of the thetas in terms of the coordinates. L was length of the member. Then we developed a relation now, and the relation was this one. This was for the individual element stiffness matrix in the structural axis. So S1, 1, 2, 1, 3, 1, this one, if you remember in terms of the coordinates, we developed this. If you remember, this first column was coming when we were giving a unit displacement at end J along the X-axis. The first column was generated, then it was at J and along the Y-axis, then at K and along the x-axis, and then along the K and along the y-axis. And then in terms of the trigonometric function, we wrote this one again. This is cos theta and this is sin theta. So you need to now change these things. So this is actually cos theta. Make this changes. And the other one is, this one is sin theta. So next now, it is individual element stiffness matrix, and it is in the global coordinate system. Now after this, we go to the structure stiffness matrix. Now how we fix the structure, how we form the structure stiffness matrix. Now form a square matrix whose order should be equal to that of structural deformations. Remember now how we fix the order of the structural stiffness matrix. Irrespective of the support conditions, we just take now the number of joints, and for the planar structure, if it is a truss, so we multiply that with 2 now. So that gives you the order of the structural stiffness matrix. For instance, we take a 3-node structure now. 3 nodes means irrespective of the support conditions now. We multiply this by 2. So 3 multiplied by 2 is coming 6. So 6 by 6 structural coefficient matrix now we are making. The order of the structural stiffness matrix will be 6 cross 6 now. Now place the elements of each individual element stiffness matrix framed into structure in the corresponding rows and columns of structural stiffness matrix. So from the element stiffness matrix now, exactly at the same location now we need to put the elements in the structural stiffness matrix. This is step number 2 now. If more than one element are to be placed in the same location, we'll discuss at a joint. Let's say 2 members are meeting, so it means 2 members are contributing. So here now the contribution from the one member as well as from the other member, from both members, it will be coming. So you can just add them up, you can just superimpose them. So we'll see this thing. So if more than one element are to be placed in the same location of the structural stiffness matrix, then those elements will be added. Now here you see the example now. At the bottom now, extreme left, if you see, this is one element, and this at the right it is another element. So these are now stiffness matrix of members or elements at the bottom, and at the top what do we see now? We see a structure element of a structure. Now this is structural stiffness matrix. 1 and 2 shows near and far end of the member. Here at the left side, if you see in circle 1 and 2, it means it is 1 is the starting point and 2 is the ending point of the element. So 1 1 we have 1 2, we have 2 1, and we have 2 2. This is from element number 1 now. This is element number 1 stiffness matrix. And here the element 2 now it is connectivity from 2 to 3 member. Now it is having connectivity from 2 to 3 now. So we have this now 2 3. This will be 2 2. This will become 2 3, 3 2, and 3 3 now. Now how they are going to be added now, these 2 element stiffness matrices, to make a structural stiffness matrix now, which is here. And the order, if you see, it is now 3 cross 3 now. So 3 cross 3, how this will be made? Now you see here, this element definition is 1 1, first row, first column. So this 1 1, we are bringing it to the 1 1 position now in the structural stiffness matrix. this element definition was first column and second row, so 1 and 2. So it is going to the 1, 2 position now here. Now this one, it is 2, 1 now, so it is going to the same 2, 1 position. This was 2, 2, so this is going to the same 2, 2 position in the structural stiffness matrix. Now, how the element number 2 members will be added? This now, if you see, this coefficient is 2, 2. So from here, it is going to 2, 2 location. Now, you see here. So it means at 2, 2 location, we have contribution from element number 1 and we have contribution from the element number 2 also. Now this one is 2, 3. So if we see here, this is going to the same location 2, and this is the third column, so 2, 3 location. Similarly, this one is 3, 2. So it is going to the 3, 2, and this is 3, 3. So this is going to the 3, 3 location. It means at joint 2, we have now these 2 members connected. So they are contributing to this 2, 2 location. If you see here, this 1, 3, we don't have any element. At 3, 1, we don't have element. It means they are not, members are not connected at these locations. They don't have any connectivity, so they are not contributing to the 3, 1 and 1, 3 position. 3, 1 and this 1, 3 position. So this is how we will make from the member stiffness matrix, the structural stiffness matrix. They will be added up. So when we get to the real problems, we'll be discussing it, but this will be running in the background. Here now you see this was K1. K, this subscript 1 is showing this is for element 1. This is the stiffness coefficient matrix of element 1, which is 1 and 2. These are now the displacement K1. When you give displacement in one direction, this first column, when in second direction, second column is generated. And why in rows also we have 1 and 2? Because it is going to be a symmetric matrix. K2, now you see what is the address. It is 2 and 3. And here in column also we see 2 and 3. And these are the coefficient. Now when we add them up, this K is the structural stiffness matrix. K1, it is the first elemental stiffness matrix. This is the second. Now we are adding them up. So at 1, 1 position, we are writing this K1. You see here 1 and 1 position K1. Now at 1, 2 position, it is minus K1. So minus K1 is coming. Now this one, now this is 2, 1. So minus K1 is coming. This is 2, 2. So K1. This you see here, this K1, it is coming from this 2, 2 position. Now, all these elemental 1 matrix, it has been accommodated in the structural, this coefficient matrix. This is the structural coefficient matrix. Now, let's take care of this K2 now, because we need to add this one up also. So now we have 2, 2. This K2 plus K2, it is actually 2, 2. So this 2, 2, you see here, this K2, it is coming from this 2, 2 position. Then we have this 2, 3, and 2, 3 is minus K2. So at 2, 3 position, we have minus K2. This one is 3, 2. So 3, 2, if we see, this one is third row and second column, and it is minus. So third row and second column, it is here, minus K2, it is coming here. And this is 3, 3. So 3, 3, we have accommodated this. So each one is coming to its own address now in the structural coefficient matrix. We were not having any one here at 1, 3 location and 3, 1 location. So we put 0, 0 here. All this process you can see here at the right side in the orange color. In the matrix, the element in the second row and second column, second row and second column, this position we are talking about. Second row and second column is K1 plus K2, where K1 is for member 1 and K2 is for member 2. This is because both K1 and K2 have structural coordinates 2, 2. So 2, 2, they are connected here, both are contributing, so that's why they are adding it up. Yeah. But now the idea of this, the purpose of showing this slide is how we add up these elemental stiffness matrices to make a structural stiffness matrix. So let's go to the next slide now. Now, example, now here an actual truss is given now. At the truss top, if you see 11.5 and 12, if these loads are given, you can see the distance is L by 2, L by 2, and 2L by 3. These are now defining these nodes now. So this is example 1 now. Here at this top location, we have these displacement. I would like to have this 2 also in the upward direction. So rightward and upward we take positive. So you just reverse the direction of this 2. So this 1 and 2, these are showing horizontal and vertical displacements at the top node. Now here at the right bottom, if you see 3 and 4, again the global displacement, and 5 and 6. So horizontal followed by the vertical. This is our notation. In circles now, if you see the member numbers now. So these are the members number, member 1, member 2, member 3. Now member 1 connectivity, it is from this bottom left joint to the top. You see this arrow. So this arrow is given here. Now, member 3, if you see connectivity is from right to left. Now you see arrow. And here this member 2, it is from the top to the right. This arrow is coming here. Now here, now if we split them at joint, so you can write the joint coordinates now. This was x1, x2. So this is my origin. So member 1 is now 0, 0. And at the top, horizontal is L by 2 and vertical is 2L by 3. So the coordinates we have at the top joint also. And here you see those displacements are shown 1 and 2. Member 2 now, if we look at, so here we have L by 2 and 2L by 3 like we did here. And at the bottom, horizontal, it is 0. Horizontal, it is L by 2 plus L by 2 means L. So L is here. And vertical, it is at the 0 level, so we have 0. Similarly, this joint 3 now, if we see, so it is 0, 0, which was here, and it is L and 0. So this is how we put the coordinates now. Now, what we will do now, first to generate, now we talk about member 1 now. To generate its elemental stiffness matrix, what will we do? First, you determine which is your starting point. So the arrow is pointing from the bottom to the top now. So it means this bottom where we have 5 and 6, this is your starting point and this is ending point. This is the start, this is the end now. So means first we need to give horizontal displacement followed by the vertical. Horizontal displacement is 5 and vertical is 6. Then we come to the 1 displacement followed by the 2 displacement. Now what will be the address of this element now? Element 1 means at the top in circle we will put 5 and 6, then 1 and 2. Let's confirm this from the next slide. So you see 5 and 6, 1 and 2. Why 5 and 6? This was the starting end, horizontal followed by the vertical. And we are using the same theta now. Counterclockwise, we find out the theta and just we are putting the value of theta in that equation. If you remember EA over L and cos square, sine square, minus cos square and sine square theta, something like that. So here you see in horizontally and vertically the same order we are following. 5, 6, 1, 2, 5, 6, 1, 2. First column, when we give displacement in the horizontal direction at the starting end, which is 5 displacement. So first column is generated. In the vertical direction, which is 6, when displacement is given, so this is generated. Then corresponding to 1, when displacement is given, this is generated. And similarly this one. Now let's confirm the address of this K2 now. K2, 1, 2, 3, 4. So let's see now, let's go to element 2. So you see here, this was the starting. Why the arrow? It is pointing from top to bottom now. So means it is the starting. So 1, 2, 3, and 4. So the address, it is verified. Next now, let's now confirm the address of this 3 3, the arrow is from left to right now, so it means it is the starting point. So its address should be 3, 4, 5, and 6. 3, 4, 5, 6. Let's see now. 3, 4, 5, 6. This is how we give the address. Equation already we know. Equation is EA over L, and then in parentheses, if you want to go and see that, so we need to confirm also some values. So let's confirm so that you have the confidence. The equation, if I go, the element equation was this one. This is the equation now. So quickly you write the first now, this first column now. It will be EA over L cos square cos sine minus cos square minus cos sine. Quickly you write it down. Cos square cos sine minus cos square minus cos sine. Now coming to, let's find out this angle now. And how angle is found? From the positive axis in the counterclockwise direction we find the distance. So it will be shift tangent inverse of 2 divided by 3 and then divided by 2. L by 2 means it will become multiplied by 2 then. So it is shift tangent inverse 0.67 I put and then divided by 0.5 I put. So this is coming 53.26. 53.26 degree. Now we were having cos square theta. So here this one now it should be coming from the cos square theta now. So how much this is coming? Mr. CR, how much is it is coming?
Yes, sir.
कितना आ रहा है? पहले आप थीटा आप मुझे बताएं, how much the theta is coming?
सर मैं मोबाइल में कैलकुलेट कर रहा हूँ, वो वैल्यू -0.70 दे रहे हैं सर, जो थीटा आ रहा है. हेलो.
हाँ आवाज आ रही है आपकी.
सर कैलकुलेटर में सही कैलकुलेट नहीं हो रहा. मैं
अपना कैलकुलेटर नहीं है आपके पास?
सर है, कैलकुलेटर है, मैं मोबाइल में कैलकुलेट कर रहा था, वो वैल्यू 0.70 दे रहा था सर.
सैयद मोहम्मद हुज़ैफा.
यस सर.
आप कैलकुलेट करके दे देना ये नंबर मुझे. थीटा कितना है? Everybody should
चेक
be
करता हूँ सर।
calculating. हाँ
सर
सर मैं चेक कर रहा हूँ
53.13 डिग्री।
कितना आ रहा है?
53.13 डिग्री सर।
अच्छा 53.13 और फिर वो से कर ले ई ए और एल स्क्वायर, तो cos स्क्वायर थीटा आ रहा है ना पहला।
यस सर।
ये नंबर वेरीफाई कर लें।
$0.541 सर।
ये 3 अगर हम यहाँ पे देख लें, लेट्स वेरीफाई दिस वन, इट विल बी इजी टू वेरीफाई दिस वन नाउ। सो 3 पे क्या है सिचुएशन, लेट्स सी द एंगल देयर। Here, if you see how much is the angle now, angle it is making 180 degree. This at the starting point we are coming and taking this angle. So this is now 180 degree. So what is cosine of square 180? Cosine
-1.
180. This is -1 if we take it square. So it is becoming 1 now. So it is, you see here this one. What is sine of 180? It is 0. So cos 180 sine of 180, it will be coming 0. Similarly, you can find out these numbers also. So this is just the matter of finding out the theta. Now, Mr. Hamza, are you there?
यस सर।
अच्छा, आप मुझे ये बताएं ना कि यहाँ पे आप एंगल कैसे लेंगे, मेंबर 2 पे आप एंगल कैसे लेंगे? How we take angle at this for member 2? कुछ है अंदाजा आपको? देखिए पहले आप स्टार्टिंग पॉइंट पे आएंगे। स्टार्टिंग पॉइंट आपका क्या था, जहां पे आपका ये 1 और 2 डिस्प्लेसमेंट आ रहे हैं। इस एरो से आप अंदाजा लगाएंगे कि यहाँ से आप टॉप से स्टार्ट हो रहे हैं और बॉटम की तरफ आ रहे हैं। स्टार्टिंग पॉइंट पे आप आ गए तो अब यहाँ पे पॉजिटिव एक्स एक्सेस आप ड्रा कर लेंगे। पॉजिटिव एक्सेस आ गया तो अब आप जाके काउंटर क्लॉकवाइज आप एंगल ड्रा करेंगे जो यहाँ पे टच करेगा। सो यू आर मूविंग इन द काउंटर क्लॉकवाइज डायरेक्शन एंड टचिंग दिस वन। आसान तरीका क्या है कि आप ये एंगल मालूम कर ले और 360 से आप माइनस कर ले, तो जो भी एंगल आ रहा है दैट इज बिकमिंग योर थीटा इन द एलिमेंटल स्टिफनेस मैट्रिक्स। उसी से आप कैलकुलेशंस करेंगे। अब आप समझ गए कि नहीं?
यस सर।
अब यहाँ पे 3 पे ये देखिए मैं 180 क्यों ले रहा था, क्योंकि स्टार्टिंग पॉइंट यही था जहां पे 3 और 4 डिस्प्लेसमेंट्स आपके आ रहे हैं। अब पॉजिटिव एक्सेस हम ड्रा कर लेंगे और इससे काउंटर क्लॉकवाइज ड्रा करेंगे। ये काउंटर क्लॉकवाइज एंगल ड्रा करेंगे तो क्या होगा, ये एंगल आपका आ रहा है 180, इसलिए मैं 180 से एलिमेंट 3 का चेक कर रहा था। ठीक है, सो यू कैन वेरीफाई दीज नंबर्स नाउ अकॉर्डिंगली। ये एड्रेसेस है आपके पास। अब देख लें इसमें पोटेंशियल लोकेशंस जो है, यहाँ पे अगर आप 5-6 पे देख ले तो 2 एलिमेंट्स आपके कंट्रीब्यूट कर रहे हैं। 3-4 पे देख ले तो 2 एलिमेंट्स आपके कंट्रीब्यूट कर रहे हैं। आप 1-2 पे देख लें तो आपके 2 एलिमेंट्स कंट्रीब्यूट कर रहे हैं। तो अकॉर्डिंगली अभी आपका क्या होगा, अभी आपका स्टिफनेस मैट्रिक्स भी आएगा। ये अब इसका ऑर्डर क्या होगा, स्ट्रक्चर स्टिफनेस मैट्रिक्स का इसका ऑर्डर होगा 6x6। वाई 6x6? अगर यहाँ पे आप देख लें दिस वन, तो क्या हो रहा है, ये देखें 3 नोड्स है आपके और 3 नोड्स पे टोटल कितने डिस्प्लेसमेंट है? 6 डिस्प्लेसमेंट है। सपोर्ट कंडीशन को अभी हम नहीं देख रहे हैं, सपोर्ट कंडीशंस का बाद में हम डिसाइड कर लेंगे। तो इसका क्या है 6x6 हम स्टिफनेस कोएफिशिएंट मैट्रिक्स में स्ट्रक्चर स्टिफनेस कोएफिशिएंट मैट्रिक्स बना देते हैं। किस तरह बनाते हैं? हर एक एलिमेंट का स्टिफनेस मैट्रिक्स ऑर्डर क्या होगा? वो 2x2 होगा। देखिए यहाँ पे भी दो यहाँ पे डिस्प्लेसमेंट है, दो बॉटम पे, दो एलिमेंट 2 पे आप देख लें दो टॉप पे डिस्प्लेसमेंट है, दो बॉटम पे। इसी तरह एलिमेंट 3 का देख लें तो इसका भी 4x4 बन रहा है। तो एलिमेंटल क्या है? In case of the pin jointed frame, the order of the stiffness matrix will be 4x4, जो कि यहाँ पे आप देख रहे हैं। देखिए 4x4, 1 2 3 4, 1 2 3 4। यहाँ पे देख ले 4x4, 4x4। लेकिन स्ट्रक्चरल का क्या होगा? It will be 6x6 ना। अब यहाँ पे देख ले ये 0.864 किस तरह आ रहा है? तो 1 1 पोजीशन है, तो यहाँ पे आप देख ले 1 1 पोजीशन पे आपका क्या है? 1 1 पोजीशन पे हमारा आ रहा है 0.432। तो लिख लेते हैं, एक यहां से हो गया 0.432 प्लस। अब दूसरा पोजीशन आप देख ले, यहां पे देख 1 1 पोजीशन एलिमेंट 2 में भी आपका आ रहा है, जो कि है दिस इज 1 1 पोजीशन नाउ which is again 0.432, so plus 0.432 जो कि 0.864 आ रहा है। अब आप देख लें स्ट्रक्चर स्टेटमेंट 0.864 ये इसी तरह कैलकुलेट हुआ है। दूसरा अगर आप कैलकुलेट करना चाहते हैं, लेट्स ये 66 वाला जो है ना, जो 0.768 आ रहा है, इसको थोड़ा सा वेरीफाई कर लेते हैं। तो यहां पे देख ले 6 और 6 पोजीशन में ये 0.768 आ गया। यहाँ पे है ही नहीं आपका 6 एलिमेंट, यहाँ पे आपका 6 एलिमेंट है लेकिन 0 कंट्रीब्यूट कर रहा है, तो दैट इज व्हाई इट इज 0.768। इसमें और आप मुझे बताएं कि कौन सा हम वेरीफाई कर लें। Somebody, you should be asking me that let's verify. This is a big number now. Let's verify this one, which is 3 तो 3 को हम देख लेते हैं। 3 यहाँ पे एलिमेंट नंबर 1 से है ही नहीं इसका कंट्रीब्यूशन। एलिमेंट 2 में अगर आप देख लें तो 3 पे आपका 0.432 आ रहा है, तो मैं इसको लिख लेता हूँ अपनी कैलकुलेटर 0.432 प्लस यहाँ पे देख ले है कहीं पे, हाँ बिल्कुल है, ये 3 पे देख लें ये कितना आ रहा है 3 यही 1 है, सो प्लस 1, सो इट शुड बी 1.432। यहाँ पे देख लेते हैं 1.432। This is how the structural stiffness matrix it is made out of these elemental stiffness matrices. तो elemental stiffness matrices में हम क्या करते हैं? We identify the element, इसका starting point, end point हम identify कर लेते हैं। Starting point पे अपना angle आप establish करेंगे। कैसे आप establish करेंगे? You take the x-axis, positive x-axis, and go in the counterclockwise direction and touch the element starting end पे। वही आपका एंगल हो जाता है, जो कि आपके पास बेसिक इक्वेशन है एलिमेंट स्टिफनेस मैट्रिक्स का EA और L, and within then we have that matrix cos square, cos sin, minus cos square, cos sin, and similarly the other columns. So थीटा, वही थीटा वहां पे हम पुट कर लेते हैं, और आपका लेंथ भी आपके पास होता है, ये सारी चीजें होती है। तो हम क्या कर लेते हैं, इसको हम वहां से कंप्लीट कर लेते हैं। ये किसी ने अब डिटरमिन किया कि नहीं कि व्हाई दिस इज 0.432 ना? लेट समबडी कंफर्म दिस। चले इसको आप कर ले। एंड देन नेक्स्ट नाउ इफ यू हैव एनी क्वेश्चन रिगार्डिंग द एलिमेंट एंड दिस, तो आप कर ले। अब एलिमेंट आपके पास हो जाते हैं, उसी एड्रेसेस से आप क्या कर सकते हैं, आप एलिमेंट ट्रांसफर करेंगे उसी एड्रेसेस पे आप स्ट्रक्चरल स्टिफनेस मैट्रिक्स में। स्ट्रक्चरल स्टिफनेस मैट्रिक्स का ऑर्डर क्या होगा? जो स्ट्रक्चर का डिग्री ऑफ इंडिटरमिनेसी, टोटल इंडिटरमिनेसी, इररिस्पेक्टिव ऑफ कंसिडरेशन ऑफ द सपोर्ट कंडीशंस, हम क्या कर लेते हैं, उस सारे के लिए हम स्टिफनेस मैट्रिक्स हम बना लेते हैं। सारे एलिमेंट्स यहाँ पे आ गए, और ये हो गया आपका कैपिटल के, जो कि स्ट्रक्चर स्टिफनेस मैट्रिक्स को जाहिर कर रहा है। नेक्स्ट नाउ वी टेक एक्चुअल प्रॉब्लम। अब एक्चुअल प्रॉब्लम को हम कर लेते हैं। ये क्या है, एनालाइज द गिवन पिन जॉइंटेड फ्रेम यूजिंग डायरेक्ट स्टिफनेस मेथड। नाउ टॉप पे हम क्या देख रहे हैं, जॉइंट 1 और 2 देख रहे हैं। लेफ्ट को जॉइंट 1 हो गया, राइट को जॉइंट 2 हो गया, बॉटम पे जॉइंट 3 हो गया। जॉइंट 3 पे अगर अब आप देख लें तो राइट वर्ड डायरेक्टेड 5000 पाउंड का लोड लगा हुआ है। वर्टिकल क्या है इसका हाइट, इट इज 40 इंचेस फ्रॉम 1 to 3 हॉरिजॉन्टल डिस्टेंस इज 40 इंचेस and 3 to 4 it is 30 inches। ये 1.5 इंच स्क्वायर जो लिखा हुआ है मेंबर 1, ये बॉक्स में आप देख रहे हैं रेक्टेंगल में, ये मेंबर 1 हो गया विच इज फ्रॉम 1 to 3। एंड ये क्या है 2 to 3, इसको हम क्या कहते हैं, मेंबर 2 कहते हैं। ये 1.5 इंच स्क्वायर है, ए क्रॉस सेक्शनल एरिया है मेंबर 1 का, और मेंबर 2 का क्या है क्रॉस सेक्शनल एरिया, इट इज 2.0 इंच स्क्वायर। सो क्विकली यू ड्रॉ दिस डायग्राम। और स्टील है इसका, तो E is 30 into 10 raised to the power 6 psi। This is the modulus of elasticity। Quickly you draw this sketch and then I move to the next slide। अब पहले हम क्या करेंगे, इसमें नोडल डिस्प्लेसमेंट का डिजिग्नेशन हम देंगे कि जॉइंट 1 पे आपके कौन से नोडल डिस्प्लेसमेंट है, जॉइंट 2 पे और जॉइंट 3 पे। Next slide। Now these are the possible displacements। Now we assume as there are no, let's say, the support conditions, तो दो displacements joint 1 पे possible, दो इस पे और दो यहाँ पे। तो आपकी काइनेमेटिक इंडिटर्मिनेसी स्ट्रक्चर के लिए जो बनती है, स्ट्रक्चरल काइनेमेटिक इंडिटर्मिनेसी टोटल इज 6 degrees without looking at the support conditions। अब देख लेते हैं कि कैन वी एस्टैब्लिश सम रिलेशन बिटवीन द हॉरिजॉन्टल एंड वर्टिकल डिस्प्लेसमेंट विद दोज द जॉइंट नंबर्स। तो बिल्कुल हम कर सकते हैं। नेक्स्ट स्लाइड में अगर आप देख लें तो ग्लोबल डिस्प्लेसमेंट इन एक्स डायरेक्शन अगर आप 2 times ग्लोबल नोड नंबर -1 कर ले, सो दैट विल गिव यू द हॉरिजॉन्टल डिस्प्लेसमेंट एट द जॉइंट्स। क्या होगा जब जॉइंट 1 की हम बात करते हैं, सो इट विल बिकम 2 times नोड नंबर क्या है 1, ये पैरेंथेसिस में आ गया -1, तो 1 हो जाएगा आपका D1 होगा। जॉइंट 2 पे हॉरिजॉन्टल डिस्प्लेसमेंट क्या होगा 2 times 2, ये जॉइंट नंबर आ गया -1, तो वो 3 हो जाएगा। एंड 2 times 3 -1 5, तो ये जॉइंट 3 पे आपका नोडल नंबर 5 हो जाएगा। ये अब हम चेक करेंगे। इसी तरह y के लिए हम एक रिलेशन हम कर सकते हैं विद द डिस्प्लेसमेंट एंड द जॉइंट नंबर्स, एंड दैट विल बी simply 2 times the node number। अब जॉइंट 1 पे क्या होगा, 2 times जॉइंट 1 आपका 1 आ रहा है तो उसका D2 होगा। जॉइंट 2 पे 2 times 2 तो वो 4 होगा, और इसी तरह 3 पे 2 times 3 6 हो जाएगा। यहाँ पे शो किया हुआ ये जॉइंट 1 था हमारा, दिस इज एक्चुअली 1, दिस इज 2 एंड दिस इज 3, so you can get rid of this, should be equal to 1। this was joint 1, this one is joint 2, and this one was our joint 3, and within circles also। So D1, you see D1 horizontal followed by the vertical, horizontal followed by the vertical, horizontal followed by the vertical। Here you see we said from that simple equation that horizontal will be D1, D3 and D5, now you see that, and vertical will be D2, D4 and D6, so we say see them also। And similarly you can increase the number of joints and you can increase the number of these displacements। Now if we see now here, now from the boundary condition we are putting this, D is the displacement, so D1, D2, D3, D4, if you see here, this was a hinge support, means it was not allowing D1 in the horizontal direction as well as in the vertical direction, so means from these given boundary condition D1 and D2 are 0 and 0। Similarly here, if we see horizontally again it was a hinge support, so D3 was 0, D4 was 0, so we are putting these one। Joint 3 was free now, so D5 and D6 we don't know, these are our unknowns, so here we put the question marks now। D5 and D6 are becoming our unknowns। Now, corresponding actions now, actions, it will be shown with A1, A2 now. Corresponding to this, now at this one, we have a hinge support, so it can have horizontal reaction, it can have vertical reaction, but at this stage, we don't know how much are those reactions. So we put A1 and A2. A1 is corresponding to D1 and A2 is corresponding to D2. Similarly, A3 is corresponding to D3 and A4 is corresponding to D4. Question marks. Why? Because we don't know at this stage how much reactions, how much actions which we take as unknown reactions, how much they will be there. At joint 3, we have D5 and D6. So corresponding actions will be A5 and A6. So A5, it is 500. So let's see, it is already given now. So if we go there to the sketch now, so let's see, where is that sketch? This was this sketch. So here you see corresponding to D5, we have F5, which is in the same direction. So we take this as positive. So here now, this is 5,000 in the same line. A6, if we see, again, if we go to this A6, so A6 now corresponding to this, in the vertical direction, we don't have any externally applied load, so we put that equal to 0. So here now, we see that it is equal to 0. Means at 5, when the displacement is unknown, so our forces are known now. And where the displacement are known, which are 0, the actions are unknown, a simple relation. This way we make our D matrix an external action matrix. And what is the relation now? Relation is A is equal to S times D. D is known, A is known. Now, stiffness coefficient matrix we need to find out. So let's go to that one now. Here we give a table now, which is showing the material properties, the geometric properties, and then the node numbers also. Element number 1, E was 30 into 10 raised to the power 6 psi. Cross-sectional area was 1.5. Length, you can find out from that horizontal and vertical distance, so it is coming 56.57. Starting end, we are taking 1, and ending, we are taking 3 now, and the angle is coming 315 degrees. So you write down now 1 to 3, we have connectivity. This is your choice. Now remember, you can do from 3 to 1 also. This is your choice. We are doing it 1 to 3. So let's go now and verify this 1 to 3. So 1 to 3, this is 1 to 3, this is our connectivity. 1 is the starting point. So here we need to find out this counterclockwise angle now. Now to do this, we need the horizontal and vertical dimensions. So horizontal and vertical dimensions are here. So what we can do now to find out this counterclockwise angle, what we do, first we find out this angle now. So the angle is coming 45 degrees. You see here, I'm finding out simply this angle, which is 40 and 40, 40 horizontal, 40 vertical. So it means the angle here is 45. So 360 minus 45, which is coming 315 degrees. So this counterclockwise distance from the positive x-axis, it is coming 315 degrees. And you see here, that is why 350 degree it is written here. If somebody is saying, no, my connectivity is going to be from 3 to 1 now, from element 1. Okay, he's correct now. But when he's finding out the distance, he is coming to the initial, this starting point, which is 3. And from here, positive axis, he is finding out this angle now. And this angle is how much? If you see here, with the horizontal, it is making an angle of 45. So this will become 180 minus 45, whatever is coming, 135 or whatever, that is becoming his counterclockwise. So if you take this joint G3 as your starting point. So this 135 degrees, that is becoming your angle then. Now member 2 now, the connectivity is given now for member 2. You see here length is given, this is the cross, and now connectivity we are saying 3 to 2. It is connected and angle is 53.13. So member 2 I'm coming in 3 to 2, it is connected. So here now this is my member 2 now, and 3 to 2 we are saying. So angle we are measuring this one now with the positive axis, because I'm coming again to the starting point, and this counterclockwise, this is becoming our angle. So this angle simply will become equal to shift tangent inverse of 40 divided by 30. So this is 53.13, and if you see here, exactly the same 53.13 we have. Rest is simple now. What will be the address now of this when we generate the stiffness coefficient matrix? So here now, this is the basic equation. And the angle now here we are using with this element number 1. 1 was the starting point. There the displacements were 1 and 2. And at the member 3, the displacements were 5 and 6. You see here, these are becoming the addresses of this matrix coefficient now. Angle we are putting this 315 now, so you can verify this 0.5 now. So when we take the cosine of this 315, it is coming equal to 0.707, and if I take the square of this 0.707, it is becoming 0.5, which is here 0.5. And similarly the rest of the elements also. K1I EA over L. So EA over L I'm finding out from this one. This is becoming my EA over L values. L1 was there, A1 was there, and E was there. This is 10 to the power 6. This is how we calculate K1 now. This is the elemental stiffness coefficient matrix for member 1. Now what will be the addresses of this element 2 now? So starting point was 3 now, and here it is 5, 6, 3, 4. 5, 6, and 3, 4. So let's see now, 5, 6, and 3, 4. What was the angle? 53.3. You can again verify. Let's verify this 5, 5. So this will become cosine of angle is 53.13. So this is becoming equal to 0.6, and if I take it square, this is becoming 0.36. So this is how we get this 0.36. You can verify it, rest of the numbers also. What will be the order of the now this structure stiffness matrix? The degree of indeterminacy was 6, so it will be 6 cross 6 now. So here now you see 6 cross 6. And this is how each element is accommodated here now. From those elemented, these are coming, and we make this 6 cross 6 matrix. This is the structural coefficient matrix now. Now this is the major part now. Rest is just the rearrangement of these rows and columns, and then going to the same situation now where we have, according to the degree of freedom, this we will reduce this to that form, and then we will solve it. So till now, if you have any question, now you let me know. You can turn on your mics. When you start practicing it, remember it will need a lot of practice if you understood this already, but still it will need practice. It's very simple calculations, but you need to go in a very organized way. Even putting these elements in the structural stiffness matrix, it needs a lot of practice and a lot of attention. Here the K, it is the structural stiffness matrix, and these are the elemental, how they are added now. We have at 5, 5 and 6, 5 location the addition. So if you go there, we have 5, 5 here, and we have 5, this 6, 5 here, and element 2, and element number 1, if you see, again, we have 5, 5, this one, and then we have this 6, 6 also. This is how both the elements. And what is the reason for this? If you see in this diagram, at 5, 6 location, both members are connected. That is why both are contributing. Both members are contributing in this one. If you see at this 1, 3, and this 4, 1, and similarly 2, 3, and this 1, 4 location, we don't have any connectivity, so we should be having 0, 0 there in the structural stiffness matrix. So you see, this is your 3, 1 because no connectivity. This is your 4, 1, no connectivity. Similarly, these one, this is how, because we don't have connectivity at those locations. Okay, if you don't have any question, then this vertical and horizontal line, it has a significance now. Actually, we will be dealing with these now elements now to solve for the unknown giant displacements and to solve for the unknown support reactions. Now, apply equilibrium condition at the location of the redundant giant displacement to write equilibrium equation and solve for the unknown giant displacement. A is equal to ST. This is that action vector we generated, that matrix. A1, A2, A3, A4, those were the unknowns now where we put the question marks. 500 was the horizontal force at joint 3, and 0, we were not having any vertical force. Similarly, if you come here, so D1, D2, D3, D4, because of the Hench condition, these displacements were understood and those were 0 just by observation. At joint 3, D5 and D6 were unknown, so we are now writing this with their appropriate this. This stiffness coefficient matrix now already we generated this one, 6 cross 6 matrix. And how we form this from the elemental, so you know the addition procedure now. Now, this way now we can find out for the unknown giant displacements now. But before this, now we need to do something. You see here, this element 1 of the stiffness coefficient matrix, it is going to be multiplied with this 0, second with this 0, third with this 0, fourth with this 0. Means then when we come to the second row, again multiplication with these 4 rows will be multiplied with these 4 elements of the displacement matrix. Means it will be giving you 0 values. So means these 4 rows, it does not have any significance now because they are getting multiplied with these zeros. So we can eliminate now these rows corresponding to the known giant displacements. So here now we apply a procedure, reduce the stiffness matrix by removing rows associated with the unknown forces. These are now corresponding to the unknown forces now, these rows now. So we are going to eliminate these rows and now columns, and columns corresponding to 0 displacements. And these columns also we are now removing corresponding to the 0 displacements. So here now the columns corresponding to 0, why? Because they are getting multiplied with these numbers. So we eliminate these rows now. Why these rows? Because they are corresponding to the unknown forces, and then columns which are corresponding to the unknown giant, these to the known giant displacements which are 0. So when we draw these lines, means these we need to eliminate and these columns we need to eliminate. So we are reduced to this 2 cross 2 matrix now. And this 2 cross 2 matrix now will become equal to 5,000 and 0 is equal to this 5 element, then 5 6 element, 6 5 element, and 6 6 D5 and D6. So here now you see this is the bottom right one, stiffness coefficient D5 and D6 is equal to 5000 and 0. When we multiply the K1 and K2 already we found. So when we put those values here, this is becoming our stiffness coefficient D5 and D6 one. When we solve this, so D5 and D6 is coming out these numbers. So we found the unknown joint displacements. These are the unknown joint displacements. Okay, after this now, once we found this, we will be now going to the other slide. Here now to find the unknown reactions at joints, reduce the stiffness matrix by removing rows associated with known forces and columns corresponding to known joint displacement, that is D is equal to 0. So we are left with this matrix now, and D5, D6 already known now. So this way, when D5, D6 known, when we put the values of D5, D6, this matrix is already known. This way we find out A1, A2, A3, A4, which are the support reactions. So here in this equation, we put K1 and K2, D5, D6 already known. So when we plug in these values, A5, A1, A2, A3, and A4 are found. These are the support reactions now. So by using this method, now where is this matrix now? 0.5 if you can quickly write this equation, I'll show you from where this is coming. And already you know this now, how we take this. Minus 0.5 K1, 0.5 K1, minus 0.36 K2, minus 0.48 K2, 0.5 K1, minus 0.5 K1, D5, D6. This is, if you look at here, this is this 5, 6 here, from here that matrix we are taking. So when we multiply this, multiplied by, look, this fifth column, this element will be multiplied by D5, this sixth coefficient, it will be multiplied by D6. These are known now. So here 0.5 with this and 0.5 with this D6. Similarly 0.36 K2 with D5 and here. And what we will get now as a result when we multiply this fifth column and sixth column of the stiffness coefficient matrix, when we multiply this with the D5 and D6, we will get now A1, A2, A3, and A4. So this is simple matrix algebra now. So from these two, and it is shown here, when we multiply, we get the support reaction. Now we find out the joint displacement. We found the support reactions now, but we don't have now the member forces. So how we find out the member forces now? You see the displacements at the joints we have, but those are in the global coordinate system. Somehow if we can transform them in the member local axis system now, so whatever displacement in the local axis at one end we have and at the other end we have, if we find out the difference of those now, that will give us now the elongation or the contraction in the member now. So if we can get that elongation, increase in length or decrease in length, then we have the equation now, delta L is equal to PL divided by AE. So once delta L is known, what we can do, then we can find out how much force is now required to have this much displacement or this much increase or decrease in the member length. So for that, we need to transform these global displacement in the local coordinate system now for that particular system. So now we are going in the reverse direction. And how we do it, we use a transformation matrix now. These are now, up till now, we found now these support displacement. How much was, this is now our A1. A1, why? Because corresponding to the D1 we have A1, so it should be with the negative sign now. So let's see now, you see here negative minus 2855. So we here now in the opposite direction 2855. This is 2857. So here we see this 2857. A3 if we see, it is negative. So again it is leftward, it should be leftward directed. So we see it is leftward directed. So if we sum up these horizontal, it is balancing this 5000 load. And this last one, if you see here, it is negative. So means opposite to D4 direction, and it is minus 2857. So here we see 2857 in the downward direction. Now, member one force, now you can do now by taking the diagonal, the resultant of these two forces and inducing it here, means this is coming in tension now. But how we do it with the direct stiffness method? So for the direct stiffness method now, this we need to go through, this is now the transformation matrix or rotation matrix we call this. For the pin jointed frame, 2D frame, it will be cos theta, sin theta, 0, 0, 0, 0, cos theta and sin theta. Always this will be. So from the sample geometry, you can prove this. Now, member forces, how we find out, as we know that in global coordinates, each end of the member can have 2 degrees of freedom or independent displacements. Hope you agree with this statement. Namely, joint N has dnx and dny. This is their D1 and D2 now. N is for the near end in x direction, displacement at the near end in y direction. This is a generalized terminology now. And joint F is the far end now, has dfx, displacement at the far end in x direction and displacement at the far end in y direction. These are the 4 now possible displacements in a pin jointed frame element. Now to find member forces, we have to determine its component displacement along the member. For that, first transform the global displacement component D in local displacement and then find change in length of member, and then we have delta L is equal to PL over AE, or from that force in member will be equal to P is equal to EA over L times delta L. Delta L we found out from this operation now. And what is that? In local axis displacement near the near end, this is delta N and this is delta at the far end now along the longitudinal axis of the member now. And it will be equal to this transformation matrix cos theta, sin theta, 0, 0, 0, 0, cos theta, sin theta. And these are now the corresponding global displacements now for that particular member. dnx, dny, dfx, dfy. And delta L will be equal to now this delta N, delta F1. Once we find this delta N and delta F, we can put now we will be in a position to find this delta L, which will be equal to delta N and delta F. And what is N? N is for the near end and F is for the far end now. Now we have element 1 and element 2 now. How to apply this rotation matrix and how we do this transformation from the global coordinate system of displacement into the local coordinate system of the displacement. So here now we go. Element 1, if you remember, theta was 315 degrees. So its local delta 1 and delta 2 will become equal to this transformation matrix, which is now basic now the standard form cos theta sin theta 0 0 0 0 cos theta sin theta. What was at the starting end the displacement? There, those were d1 and d2. This is near end. So dnx, dny. So we are putting now the actual displacement d1 and d2. And what were at the far end, if you remember, joint 3 was the far end. There the displacements were 5 and 6. So we are putting d5 and d6 now for that particular member. And we know these displacements now. So we are putting now, instead of the theta, we are putting this 315 degrees. And for D1 and D2, it was, they were at joint 1 where we were having the hinge supports 0, 0. And this D5 and D6 already we found, so I'm putting just those values. Instead of D5, I'm putting 0.00623. This, all these numbers are known now, so D1 is coming 0 now. We don't have any elongation there or any decrease in size. But D2, which is a free joint, so there I'm getting this value 0.003. This is in the local coordinate system now. So our delta now will become equal to what? It will become delta 2 minus delta 1 now. This is the basic equation. How we find out this P1, this is the force in member 1 now, which will be E1 A1 divided by L1 times delta L1. E for member 1 was 30 into 10 to the power 6. Cross-sectional area was 1.5 inches square. Now delta L was delta 2 minus this 0. So delta 2 is 0.0053 minus 0. And L1 was 56.56. So when we run these numbers, it is coming 4080.80 with positive sign, means it is tension. So member 1 force, it is coming in tension and it is 4080.80. We do the same process for member 2 now. So member 2 now, if you see, theta was equal to 53.13. Delta 1 and delta 2 now, this is for element 2 now. Cos theta, sin theta, so you see the standard formation of the transformation matrix. It was connected from 2 to 3 now. It was connected from 3 to 2. So at 3, the displacements were 5 and 6. And at 2, which was the ending point, it was from 3 to 4. So here I'm putting now in the transformation matrix these values. D5 and D6 already we found. D3 and D4, those were 0, 0. So I'm putting those 0. Now the product of these two matrices, so delta 1 is coming equal to 0.00298. We are going at least up to 4 decimals now in this finding out these deltas. Delta 2 is coming equal to 0, 0. Why? Because 0 multiplied by 0, this is 0 and this is 0. So this is coming 0. Against force in member 2, which will be P2, will be equal to E2 A2 divided by L2 times delta L2. So this is E2. A was 2 inches square. Delta 2 now, this should be equal to delta 2 actually. This should be equal to 0 minus, this is now a mistake here. So delta 2 is 0 minus this 0.00. So we should have this. Well, this you can put this 0 minus this 0.00298, and this is our L2. So when we run this number, this is how we get this negative force. So member 2 force already we found by using this standard procedure. Now here you see it was in tension and this is in compression. Tension means away from the joint and this is compression towards the joint, and these two forces now we found. You can find out the stresses also now in these members. So stresses, when we go now, already the cross-sectional area we have the force in member 1, the cross-sectional area. This is how we get now the stress in member 1. Stress in member 2 now, it is now, if you see here, P2 we already found it was 2 inches square, so 7. Now, if we discuss a little bit design here, the material allowable stress was 2000 psi, right? So if you see here member 1 now, it is more than 2000. So it means you need to grow this size now. Instead of 1.5, maybe you need 1.75 or maybe 2 inches square. So then the design is coming. But design you see here now, design is based purely on the analysis. What we do in the design, it's a hit and trial method. Initially, we assume certain dimensions. We size initially on a thumb rule the size of an element and we run the numbers. Forces are coming. Now, we compare the allowable stresses with the stress demand now. If the allowable stresses, they are coming less than the actual demand, what we do, we increase the size of the member. Otherwise, we reduce it. And if they are coming right on the money, so we keep those sizes. So this is in a way now we have discussed design problem also. This is how the members are designed. We are done with this problem number 1 now. You can ask me if you have any question. Mohammad Tariq, do you have any question now?
Yes, sir.
Where is that question?
Sir, in the last slide where you explained the design procedure.
This
sir.
one? Okay, this one, okay.
Yes, sir.
So what is the question?
Sir, that in stress in member 1, sir. सर आपने कहा कि एरिया को हमने बढ़ाना होगा सर, तो वो जो स्ट्रेस लिमिट है वो हमें सर कहाँ से पता चलेगा सर? स्ट्रेस
अच्छा, इसका अपना क्राइटेरिया ना, फर्ज करे आप जाते हैं लेबोरेटरी में स्टील, तो आपने चेक किया होगा कि 40 ग्रेड का स्टील का मतलब क्या है, आपका 60 ग्रेड का क्या है, यील्ड स्ट्रेंथ तक आप चले जाते हैं ना। अब अगर यील्ड स्ट्रेंथ तक आपका डिजाइन पहुंच जाता है तो फिर आपके पास फैक्टर ऑफ सेफ्टी तो कोई भी नहीं ना। अब उससे ज्यादा लोड आप बढ़ाएंगे थोड़ा सा भी तो आपका स्ट्रक्चर फेल हो जाएगा। ये सिंपल इसका ये है कि फर्ज करे आप कहीं पे जाते हैं ना, आप कहीं पे जाते हैं, आपको 500 रुपया चाहिए आपका आने जाने का किराया, और फर्ज करे वहां पे आप खुराक करते हैं, लेकिन आप कभी भी 500 रुपए के साथ आप नहीं जाते। आप जेब में क्या करते हैं, आप 1000 रुपया आप ले जाते हैं। इसमें क्या है, फर्ज करे आपकी सवारी खराब हो जाती है, आपका कोई और साथी आ जाता है, कोई इस तरह की अनफोर्सीन, तो उसके लिए क्या करते हैं, आप वो डबल कर लेते हैं। अब मटेरियल में आप क्या करते हैं, आप इसका स्ट्रेंथ एक्चुअली ये 40 तक आपका ले जाएगा। बेंडिंग स्ट्रेसेस की हम बात कर रहे हैं, 40 के एसआई तक आपका स्ट्रेस ले जाएगा, लेकिन हम 40 के एसआई तक डिपेंड नहीं करते। हम कहते हैं कि इसको हम 66% तक हम क्या करेंगे, हम इसका बेंडिंग स्ट्रेस जो है ना वो यूटिलाइज करेंगे, और बाकी आपका 34% जो है ना वो हम रिजर्व में रख लेते हैं। जिस तरह वहां पे आपने 500 आपने क्या किया था, 50% अमाउंट आपने एक्स्ट्रा आपने साथ जो है ना वो एज ए रिजर्व रखा था। तो यहाँ पे हम क्या करते हैं, 34% हम अपने पास रिजर्व रखते हैं, तो वो आपका अलाउबल हो जाता है 66% ऑफ द यील्ड स्ट्रेंथ। अब आप समझ गए कि नहीं?
यस सर, ओके
ठीक है। तो अब क्या होगा, आप स्ट्रेसेस लेवल आप कम रिज्यूम करेंगे ना, तो आपका साइज बढ़ जाएगा, एक्चुअल से साइज बढ़ जाएगा, तो वो क्या है, आप सेफ्टी की तरफ आप जा रहे हैं फिर।
यस सर, बिल्कुल।
तो क्लियर हो गया इसमें आपको?
यस सर क्लियर हो गया।
अब अगर वो अलाउबल भी आपका मीट नहीं हो रहा ना, तो इसका क्या है, ये देखे 1.5 आपका डिनोमिनेटर में आ रहा है ना, तो
यस
इसका
सर।
तरीका क्या है कि ये 1.5 आप अगर ज्यादा करेंगे तो आपका ये स्ट्रेस क्या है, वही 2000 की तरफ आएगा। तो वो आप एरिया मालूम करेंगे जिसमें ये 2000 या 2000 से जस्ट बिलो हो जाए।
ओके सर, समझ आ गई सर।
अच्छा, नेक्स्ट मिस्टर सुलेमान, डू यू हैव एनी क्वेश्चन?
नो सर।
मिस्टर मोहसिन खान?
नो सर। सर प्रोसीड फर्दर सर।
अच्छा, शाम मसूद है आपका कोई क्वेश्चन?
नो सर।
अच्छा, अगर आप नो सर कह रहे हैं ना, तो क्विकली नाउ आई विल रन ओवर टू अदर प्रॉब्लम्स। वहां पे देखेंगे, वहां पे आप देख लें, इफ यू हैव एनी प्रॉब्लम so you can stop me, you just turn on during the presentation, you can stop me now that I need this explanation now. Okay, so we go to the next one. And other thing now, if you can arrange one more class before the Eid now, so that will help. When that is possible.
सर सीआर आपके साथ फिर कांटेक्ट कर लेगा वो।
चले ठीक है, मेरी अवेलेबिलिटी भी देख लेना। नोमान, you just coordinate. It is not possible tomorrow from my side, and other than tomorrow, then you can tell me that we will be available this time, so that we can finish this and find this direct stiffness method.
Okay, sir.
Acha, now we go to the next one now. So here now, you see here quickly, you draw this sketch now. I'm going to now quickly explain this one. It's again two members problem with three nodes, node 1, 2, and 3. When we put these circles now, node numbers in circles, we don't need to label them as A, B, and C. We don't need to repeat these things. So 1, 2, 3, ये A, B, C से आप हटा सकते हैं। Again, ये rectangles में जो आप देख रहे हैं, these are the node numbers now. 3 पे अगर आप देख लें, 20 to the right and 40 downward directed, we have loads. 1 is a hinge support and joint 2 is a hinge support. 10 feet from 1 to 3 horizontal distance, 3 to 2, now horizontal distance is 20 feet. Now joint 1 vertical, we have 10 feet from 1 to 3 now, and from joint 2 to 3 we have 20 feet. Now means 1 and 2 are not at the same level. If you are done with the sketch now, I move to the next slide. E, a constant for both members. In the previous, it was not constant. For member 1, we were having 1.5 inches square, and for member 2, we were having area 2 inches square. Okay, with this now, I go to the next slide now. So member node numbers at 1, it will become now D1, D2. At 2, D2, D3. At 3, it will become this was D3, D4, so this will become D5, and D6 will be vertical. So here now, these are now the unknown joint displacements. It's a 6 degrees because we have 3 nodes. Now these are how we apply now those relation. And here now we see adjoint 1, D1, D2, D3, D4, and D5 and D6. So means joint 3, which is having D5 and D6, these are free. This is free one. We don't know displacement, so we record D5 and D6 at unknown. D1, D2, D3, and D4, we have 0, 0. Now here, let me explain you one thing. If you start node numbering from 3 now, we are keeping now the free joint at the end now. What is the purpose of putting this at the end. Now we could have started now joint numbering from this free end and could have moved to the where we have restraints. The purpose of this is we are putting this free joint at the end so that when we reduce the structural stiffness matrix, we should be having that reduced matrix at the right bottom. That those elements are coming in the right bottom. If we start from here, this is joint 1, so this will become D1, D2. So now your that reduced matrix will come to the left top now. And if you scatter this, if you select this free joint in between, so these coefficients will be coming then in between. So you will be looking for them now. Let me look at them. Where are those free? So we need to move in an organized way. We will take an example where it will be accommodated in the left top corner. So now the action matrix, so A1, A2, A3, this A4, A1, A2, A3, A4, you should be looking at the cursor. These are unknowns because these are the support reactions. A5 and A6, A5 corresponding to D5, it is 20. So let's see now, right, what directed 20 we have or not. So yeah, this 40 is downward corresponding to D6 now. So, but D6 we took in the upward direction, it is upward direction. So we take this A6 in downward, which is negative, opposite to this D6. So we have now D matrix and the action matrix also. S is now left, so let's generate the S matrix. Here the connectivity, if we take from, let's see, from this one 1 to 3 we are taking, and from here 2 to 3 we are taking. This is from 2 to 3 and this is from 1 to 3. So the one element address will be now D1, D2, D5, D6. 1, 2, 5, 6 for element 1. So element 1 FVC 1, 2, 5, 6. Element 2 address from here, it will become, this is 2 to 3 we are saying. So this will become 3, 4, 5, 6. So here we see now this is 3, 4, 5, 6. If you are taking connectivity of this member now from 3 to 2, so your address will become 5, 6, 3, 4. Right? But here now in the table we are defining this one. Let's confirm for element number 1 this 45 degrees now. So 1 to 3 we are saying. So 1 to 3 I am coming. This is 1 to 3. So means in the counterclockwise direction, this angle we need to find out. Let's look at the dimension of this. So the dimensions are here, 10 and 10. Look, 10 horizontal, 10 vertical means it is 45 degrees. So let's see now. So this is 45 degrees. 2 to 3 now we need to find out angle, this member 2 angle, 2 to 3. This is 2 to 3 now. So 2 to 3 if I go, this is my counterclockwise direction angle. You see here this. So 2 to 3, this is now 90 degree and we are going now 90 degrees. So it is, we can find out this distance. From 180 we need to subtract this angle. So this is how we can find out this angle, which is 135, which is making sense now. Now next, now the elemental stiffness matrix is generated. So it's just for element 1 putting the value of this theta here. This is, we are putting the value of theta here and generating these values. Similarly for element 2 now, we are putting this 135 in that basic equation. And this. Now K1 plus K2, so this is how we are adding them up now and generating this 6 cross 6 matrix. Next now, we are going to this equilibrium equation now. A already we generated, D already we generated. Now we have this. We are reducing this now, corresponding to unknown now forces, we are eliminating the rows corresponding to the zero displacement. We are eliminating the columns. So we are reduced to this matrix. So this D5, D6 multiplied by this bottom right matrix is equal to 20 minus 20. D5 and D6 unknown. Now we can solve this problem and we get this D5 and D6 now. Now we take these elements now, multiply these by D5 and D6, and D5 and D6 now known. So now A5, A1, A2, A3, and A4 now. So you can find out because D5 and D6 now, no. So here now D5, A1 and A2, these are known now. Now we put now these are the support reactions we put at their corresponding locations. Now we need to find out A1 and A2. Somehow now if we can find out the axial now, this increase or decrease in this member 1, and similarly the axial the now difference in this length now, so we can find out the forces. Already we know the global displacement at these joints, so we can transform them into the local displacements. And that way, if we find out the difference of these local displacements, we find out the change in length. So next now, we go now, again you see here the same process. This is the transformation of rotation matrix for the pin jointed frame element. These are the displacement, global displacements, and how they are related with the help of this transformation matrix to the local displacements. The difference of this local displacements, that will give you the change in length. Now, so member number 1 now, here we see delta 1, delta 2. These are the at the near and at the far end, these are the displacements. We D1, D2, D5, D6 already we put those numbers. For member 1, the theta was 45 degrees, so we multiply them, and delta 1 and delta 2 we have this way. And this is how the force we find out. Again, that basic equation we are using. So now we have delta 2 and we have delta 1 also. EA for member 1 we have, L1 we have. So this is force now. Because of this negative, we say it is negative. Next, we go to step number 5. Again, this step number 5 is again the transformation matrix, the global coordinates. We multiply them and get the local now displacement. So this is how it was 135. And this already we have D3, D4 were 0. D5, D6 we found. So this is how delta. Now again that basic equation for finding out the force we are using. So this is given minus 42.3. This is the compression force. We now put these compressive forces on the members. Support reactions are known, member forces are known, and this one. And now you can check the equilibrium of the joints and the equilibrium of the forces, these member forces also. So this way, this is now the finally analyzed structure. This is how we do it. Next now, it's a little bit now complicated problem, but this I'll give you as a review problem. You review it. What we take now, look here, we start from the free joint now. Joint 2 is restrained, joint 3 is restrained, and joint 4 is restrained. The member numbering also you see. This is not connectivity. This is just showing you the dimensions now. So members, you can see these thick members now. Member 1, 2 and 1 joints. Member 2, 1 and 3 joints. Member 3, 1 and 4 joints. At 4 we have hinge support. At 3 we have hinge support. At 2 we have a hinge support. What will be the order of the structural stiffness matrix now? We have 4 joints, so 4 multiplied by 2, it will be 8 cross 8. Each member will be having 4 cross 4 element stiffness matrix now. So this one, at 1 now, free joint, we are taking start from the free joint now. So your element now stiffness matrix, when you reduce it, it will be now accumulating in the top left corner of the stiffness coefficient matrix. And quickly I'll show it to you. Here, according to this, now you go by this connectivity. Member 1, so you see horizontal and vertical 1, 2. Member 2, 3, 4. Member 3, 5 and 6. Member 4, 7 and 8 displacements. Connectivity you can see now with these arrows. Member 1 is connected from 2 to 1 now. So member 1, if you see the element stiffness coefficient address now, it will be 3412. Member 1, I'm saying, let's check now. Member 1, when we go, so 3412, you see, this is the address. Member now, let's member 3C, it is connected from 4 to 1 now, so its address will be 7812. So this is, let's see now, this is 7812, you see that is now. So you select your starting point, you select the member orientation also from where, which one node to which one node it is connected. So you can verify these things now. And here in table form, now how we are getting here now, if you see D1, D2 were unknown. Yeah, this was a free joint, so D1, D2 were unknown. D3, D4, D5, D6, D7, and D8. So D4, it means we have some displacement there. So you can see there, here some settlement is given in the direction. So that is why we are putting that value there. Correspondingly, you can see the reaction, these actions also. D1 and D2, if you see, D1 and D2, corresponding to this, we don't have, only settlement is involved. So because of the settlement, we are finding out the member forces. So it means the action forces A1 and A2 are 0, 0 rest. We have the displacement, pre-displacement, it is now accommodated. D4, what now, let's see. Remove all the joints and then determine the force, this, what is happening at this. Determine the force in member 2 of the assembly, only member 2 we are asked in figure below. If the support at joint 2 settles down, it means it is going in the Y direction by this 25 millimeters. So see what is the displacement here, D4, but it is in the upward direction now. So we come to the D4 location and 0.025. This is our, so you need to put them by member lengths are in meters, so you need to put this also in meters unit consistency, that should be uniform. A1, A2, no external, it's a free joint, no loads are applied there, so we put them equal to 0, 0. A3, 4, 5, 6, why unknowns? Because those were the hinge support, so we need to find out the reactions there. So now starting point, end point, from the arrows we pick the element numbers, their lengths and their thetas also. How the thetas are made, you know about this thing also. So next now we generate the elemental stiffness matrix, how the address is, how the theta and how the L is accommodated. So you need to verify these numbers. Similarly for element 2, for element 3, then we add them up. You see here now the structure stiffness matrix 8 plus 8. So each one is now added up at their appropriate location. Then again we reduce it, and now this is what I was talking about, that your reduced stiffness matrix, it will be at the top left now. So at the top left now we have this matrix. Why? Because we started our displacement or the joint numbers from the free joint. If that is your last one, it will come here to the bottom right. It will be accommodated here at this corner. Q, again, those are those support reactions. So here we are showing this with the different notations now. When we multiply this, we now need to multiply this with this D1, D2 to get this 0, 0, and we see it here, this one. And we have this one also. So this is how all these things, D1 and D2 are known. Then we come again to the member forces. Now, these are known in the global system, so we can find out the local one by this transformation matrix. Here now, this is for element 2, all these, and with this, now you need to go through this, and if you have any question, you can ask me in the coming lecture then. And CR is going to coordinate with the class now in order to arrange now an additional class before the Eid. And it should not be tomorrow because tomorrow I have some other activities. So it can be Wednesday and it can be Thursday. Mr. Faisal, are you there?
Yes, sir.
Okay. Now, you can ask me if you have any question. Otherwise, we are done for today's class. And then those can stay only those who have YOC exam today.